Let me start with something uncomfortable. If certain modern theories in physics are correct, then somewhere in the vast structure of reality, you have already died. And somewhere else, you are still alive in situations you narrowly escaped here. That sounds dramatic. It sounds like science fiction. But it doesn't begin with fantasy. It begins with laboratory experiments. Cold, careful, repeatable experiments. To understand this idea, we have to begin not with galaxies or multiverses, but with something much smaller. An electron, a tiny particle, so small that you will never see one directly. And yet, everything around you, your body, this room, the air, is built from these invisible ingredients. Now here's where things get strange. In ordinary life, objects behave in a very predictable way. If you roll a marble across the floor, it travels along a single path. If you toss a ball, it follows a smooth arc. At any moment, it has one position and one speed. That's how the world feels. Definite, solid, singular. For centuries, physicists believed atoms and electrons must behave the same way, just smaller. Then came the double-slit experiment. Imagine you fire tiny particles, one at a time, toward a barrier with two narrow openings. Behind the barrier is a screen that records where the particles land. Common sense tells you what should happen. Each particle goes through either the left slit or the right slit, and you get two clusters on the screen. But that's not what happens. Instead, you get an interference pattern, a pattern that only makes sense if each particle behaves like a wave that passes through both slits at once and interferes with itself. Let that sink in. Each particle is fired individually. No other particles around to bump into. Yet the pattern builds up as if every particle somehow explores both paths. So what is the electron doing? According to quantum mechanics, before you measure it, the electron is not in one definite place. It exists in a superposition, which simply means a combination of multiple possible states at the same time. Not because we don't know which path it took, but because, in a very real mathematical sense, it did not choose one. Only when we measure it, when we force nature to give us an answer, does the electron show up in one specific place. This is not speculation. The equations predict it. The experiments confirm it. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions agree with experiments to astonishing accuracy. And yet, no one fully agrees on what it means. Because if the electron truly exists in multiple states at once before measurement, then we are left with a profound question. What exactly happens when reality chooses? Or does it choose at all? So what happens when reality chooses? In the traditional view of quantum mechanics, associated with the Danish physicist Niels Bohr, the answer is this: the wave function collapses. That's the technical phrase. Before measurement, a particle exists in a spread out cloud of possibilities. After measurement, it snaps into one definite outcome. But here's the uncomfortable detail. The equations of quantum mechanics do not actually contain a collapse mechanism. The Schrödinger equation, the central equation of quantum theory, describes smooth, continuous evolution. It never says, and now the wave function collapses. That part is added as a rule, a kind of patch, a practical instruction that works beautifully for predictions, but leaves us wondering what physically causes it. Collapse sounds simple, but think about what it implies. Something fuzzy and spread out suddenly becomes sharp and definite. When? Why? Does the measuring device cause it? Does a human observer cause it? Does consciousness play a role? Physicists argued about this for decades. Then in 1957, a young physicist named Hugh Everett III suggested something radical. He asked a dangerous question. What if nothing collapses? What if the mathematics is telling us the literal truth? Suppose the wave function never reduces to a single outcome. Suppose it always evolves smoothly, exactly as the equations say. Then when a quantum event has multiple possible results, all of them continue to exist, but in separate, non-communicating branches of reality. Imagine reality as a branching tree. At the trunk you have the past. As time moves forward, every quantum event causes a tiny split. In one branch, an atom decays. In another, it doesn't. In one branch, a photon goes left. In another, it goes right. At first, these splits seem microscopic and irrelevant. Who cares what one atom does? But atoms make up molecules. Molecules make up cells. Cells make up brains. Brains make decisions. So if the branching happens at the smallest scales, it inevitably scales up. Picture yourself deciding whether to send a message or not. Your decision ultimately depends on electrical signals in your brain, which depend on molecular events, which depend on quantum events. If those microscopic events can branch, then so can the outcomes of your decisions. In one branch, you send the message. In another, you hesitate. In another, you delete it. Each version of you feels continuous. Each one remembers a consistent past. But the future has diverged. This idea became known as the many worlds interpretation. It doesn't add new equations. It doesn't change the predictions of quantum mechanics. It simply removes collapse and takes the mathematics at face value. And here's the key insight if you include the observer, you inside the quantum system. Then when a measurement occurs, it's not just the particle that splits into possibilities. The measuring device splits. The laboratory splits. You split. Not in a science fiction duplication machine sense. There is no dramatic tearing sensation. Instead, there are now multiple versions of you, each entangled with a different outcome. In one branch, you see the particle here. In another, you see it there. Each version of you believes the result was random. Each feels like the only one, and none can detect the others. If this picture is correct, then the universe is not a single unfolding story. It is an ever-branching structure of parallel histories, constantly dividing at scales far too small for us to notice directly, and that brings us to a deeply unsettling possibility. If every possible outcome happens somewhere in this branching structure, then every possible version of your life also happens somewhere within it. If every possible outcome happens somewhere in this branching structure, then we have to follow that idea wherever it leads, even into uncomfortable territory. Consider something simple and ordinary. You're driving home at night. A car runs a red light. In your experience, you brake just in time. Your heart races, but you're fine. You go home. You tell someone about the close call. That feels like a single event with a single outcome. You survived. But in a branching picture of reality, survival was not the only physically allowed outcome. There were other possible trajectories of atoms, other arrangements of timing and motion. In some branches, the braking happened a fraction of a second later. In some, the angle was slightly different. In some, the collision occurred. If the wave function never collapses, if all allowed outcomes continue, then those branches exist just as legitimately as the one you remember. So in that very literal sense, there are branches of reality in which you did not make it home. Now here is the crucial point: you do not experience those branches. You can't. Experience requires a functioning brain. Memory requires physical continuity. In any branch where your biological processes permanently stop, there is no ongoing awareness to register that fact. From the outside, from a hypothetical view of the entire multiverse, there is a vast branching structure containing versions of you that live, versions that die, versions that take radically different paths. But from the inside, from the only perspective you ever have, you trace a single continuous line. Think of it like this. Imagine a massive railway network that splits again and again into countless tracks. At every junction, the train divides perfectly into two identical trains, each continuing on a different track. Now imagine you are a passenger on one of those trains. You never feel the split. You simply continue forward on your track. Other versions of the train move along other tracks, but you have no window into them. Your conscious experience is like riding one track through an unimaginably complicated network. This idea has led some thinkers to speculate about something called quantum immortality. The rough idea is that if there are always some branches in which you survive, then from your subjective perspective, you might only ever find yourself in those surviving branches. But we need to be extremely careful here. First, this is not experimentally verified. It is a philosophical extrapolation from a particular interpretation of quantum mechanics. Second, Survival in some technical sense does not imply health, youth, or anything like the dramatic versions portrayed in fiction. The mathematics does not promise comfort. It merely describes branching possibilities. More importantly, we do not yet understand consciousness well enough to say how it relates to branching wave functions. There is no accepted physical theory that explains why a particular stream of awareness would follow one branch rather than another. In fact, in the many worlds picture, all branches simply contain their own version of you, each equally real. So when we say, "You're already dead somewhere else," what we really mean is this: within the full mathematical description of reality, there exist branches consistent with physical law, in which your life ended at earlier points. But those branches are not ghostly afterlives. They are not accessible parallel rooms. They are simply parts of a larger quantum structure. The unsettling part is not mystical, it's logical. If every allowed outcome happens, then every allowed version of your story is written somewhere in the structure of reality. And yet, you will only ever read one of them. At this point, it's important to slow down and ask a hard question. Are we still doing physics, or have we drifted into philosophy? The many worlds interpretation, proposed by Hugh Everett III, makes exactly the same experimental predictions as the more traditional Copenhagen interpretation associated with Niels Bohr. If you run the double slit experiment, both interpretations give you the same interference pattern. If you calculate the probability of finding an electron in a certain place, both give you the same number. No experiment performed so far can distinguish between them. That's a remarkable situation. In most of science, competing theories eventually produce different predictions. One says the planet will be here, the other says it will be there. You look through a telescope and find out who was right. Here, the mathematics underneath is identical. The disagreement is about what the mathematics means. Copenhagen says the wave function is a tool for calculating probabilities. When a measurement occurs, it collapses to a single outcome. That collapse is not described by the Schrödinger equation. It's an additional rule that connects math to observation. Many worlds says there is no collapse. The Schrödinger equation is always valid. When a measurement happens, the system evolves into a superposition of observer plus result states. Each term in that superposition corresponds to what we call a branch. Both views work operationally. Both let engineers build lasers and transistors. Both allow us to predict atomic spectra to extraordinary precision. So what is the disagreement really about? It's about ontology, about what exists. Does only one outcome become real? Or do all outcomes remain real in separate branches? This is where humans start to feel uneasy. We are comfortable treating equations as calculation tools. We are less comfortable when those equations seem to describe a reality far stranger than common sense. There is also a deeper issue: what counts as a measurement? In the laboratory we talk about detectors and screens, but those are made of atoms, and atoms obey quantum mechanics. So if everything is quantum, where exactly does collapse occur? At the detector, at the eye, at the brain, at consciousness. Physicists have debated this for nearly a century. Some interpretations introduce hidden variables. Some modify the equations to include objective collapse mechanisms. Others accept decoherence, the process by which quantum systems interacting with their environment rapidly lose interference effects, as explaining why branches don't visibly interfere with each other. Decoherence is experimentally well supported. It explains why macroscopic objects appear classical, but it does not, by itself, select a single outcome. It explains why branches stop talking to each other, not why only one is real. So we are left with an unusual situation in science. The predictive core of the theory is rock solid. The interpretive layer is unsettled. When people hear multiverse, they often imagine bold claims about other worlds being proven. That's not accurate. What we have is a mathematical framework that works spectacularly well, and multiple ways of understanding what that framework implies about reality. Saying, "You are already dead somewhere else," is not an experimentally confirmed statement. It is a consequence of taking one particular interpretation, one that removes collapse completely seriously. And intellectual honesty requires us to say that clearly. We are exploring possibilities that arise from our best equations. We are not reporting a photographed parallel universe. The mystery is not that physics has gone mystical. The mystery is that our most successful theory leaves room for radically different pictures of what is actually there. Even if you remain skeptical about quantum branching, modern cosmology introduces another route to a similar, unsettling conclusion. Let's zoom out far beyond atoms, beyond stars, beyond even our observable universe. In the late 1970s and early 1980s, a theory called cosmic inflation was developed, most notably by Alan Guth. Inflation proposes that in the earliest fraction of a second after the Big Bang, the universe underwent an extremely rapid expansion, faster than the speed of light. Not objects moving through space faster than light, but space itself stretching. This idea wasn't invented to create multiverses. It was proposed to solve specific problems. Why the universe looks so uniform in temperature in all directions, and why its geometry appears so flat. Inflation explains those features beautifully. And importantly, its predictions about tiny fluctuations in the cosmic microwave background have been confirmed with impressive precision. But some versions of inflation lead to something even more dramatic. In certain models, inflation doesn't stop everywhere at once. It stops in patches, forming bubble universes, where stars and galaxies can form. But outside those bubbles, inflation continues. Space keeps expanding, spawning more bubbles endlessly. This is called eternal inflation. If that picture is correct, then our observable universe, everything we can see with telescopes, is just one small region in a vastly larger cosmic structure, possibly infinite. Now here's where simple combinatorics enters the story. There are only so many ways to arrange particles within a finite volume like our observable universe. The number is enormous, unimaginably large, but not infinite. If space itself is infinite, and matter is distributed throughout it, then those finite arrangements must eventually repeat. It's like shuffling a deck of cards. There are about 1068 possible orderings, a gigantic number. But if you shuffled enough times, eventually you would get the same sequence again. In an infinite universe, with enough regions the size of our observable cosmos, the exact arrangement of particles that makes up you could occur again. Not approximately, exactly. Somewhere unimaginably far away, there could be another Earth. Another version of this planet with the same continents, the same oceans, the same history, at least up to some point. And on that planet, someone physically identical to you, with the same memories up to this moment, might be watching a similar explanation. This is not quantum branching. This is simple statistical reasoning applied to a potentially infinite cosmos. Of course, we must be cautious. We do not know whether space is truly infinite. We do not know whether eternal inflation is correct. These are active areas of research. The evidence for inflation is strong, but the extrapolation to an infinite multiverse goes beyond what we can directly observe. Still, the possibility forces us to confront a strange idea. Even without quantum mechanics splitting timelines, sheer size alone might duplicate you. In that distant region, events could unfold differently. A random asteroid impact might have occurred there, but not here. A disease might have spread differently. A tiny fluctuation in early conditions might have cascaded into a different outcome. So when we talk about, you're already dead somewhere else, there are actually two independent scientific pathways that gesture in that direction. One comes from quantum mechanics and branching wave functions. The other comes from cosmology and the potential infinity of space. Neither is confirmed in the sense of direct observation of other universes. But neither is fantasy pulled from nowhere. They are logical consequences of extrapolating well-tested theories beyond the narrow window we can directly see. And what makes this difficult is not just the scale. It's that both roads suggest something deeply counterintuitive, that what feels singular and unique from the inside may be one instance among countless variations in a reality far larger than we ever evolved to imagine. Now let's slow down and run a careful thought experiment. Imagine a vast library. Not an ordinary library with thousands or millions of books, but a library containing every physically possible biography of you. One book describes your life exactly as you remember it, page by page, moment by moment. Another book is identical until you were 7 years old, and then one small event changes. You took a different step. You made a different friend. The rest of the story unfolds differently. Another book is identical until yesterday. Another diverges 10 years from now. Some biographies are only slightly different, a different job, a different city. Others are dramatically different, different health outcomes, different lifespans, different turning points. If the universe is single and finite in its history, then only one of those books corresponds to physical reality. The others are just unrealized possibilities. But in a branching quantum picture, or in an infinite cosmological picture, many, perhaps all, of those books correspond to real physical histories somewhere in the structure of reality. Here is the subtle and important point. Every version inside its own book experiences life as singular. Open any one biography at random. The you inside that story remembers a consistent past. That version does not feel like a copy. It does not sense branching points. It does not feel alternative versions running alongside it. It simply experiences continuity. This tells us something profound about consciousness. Whatever consciousness is, and we do not yet have a complete scientific theory of it, it appears to be local. It is tied to a particular physical process unfolding in time. When the brain in one branch follows a certain chain of events, the experience tracks that chain. If a different chain unfolds elsewhere, that branch contains its own stream of experience. There is no evidence that awareness floats above the branches, selecting between them. There is no known mechanism by which information transfers from one branch to another once decoherence has separated them. From the inside, reality always looks single-threaded. This helps explain why the idea of multiple versions of you feels so alien. Your brain constructs a narrative identity, a story that connects your memories into a coherent line. That narrative is powerful. It gives you the sense of being one continuous self moving from past to future. But even in ordinary biology, that continuity is less solid than it appears. The atoms in your body are gradually replaced. Neural connections rewire. Memories fade or distort. You are already a dynamic process rather than a fixed object. If reality branches, then you may be better understood not as a single line, but as a pattern that can, under certain interpretations of physics, instantiate in multiple diverging ways. Think of a whirlpool in a river. The water molecules flow in and out constantly, but the pattern persists for a time. If the river splits into two channels, similar whirlpools might form in both. Which one is the original? The question may not have a clear answer. Likewise, if the universe allows multiple instantiations of your physical pattern, each with its own continuity of memory, then identity becomes less about uniqueness and more about structure. This doesn't make your life less real. It makes reality larger than the narrative container your intuition prefers. And perhaps the real difficulty is not accepting that there could be many versions of you. It is accepting that the sense of being a single, indivisible thread might be a feature of perspective, not a fundamental feature of the universe itself. At this stage, it's essential to separate imagination from established knowledge. Physics is powerful, but it is not magic. So let's carefully list what we actually know and what remains uncertain. We know that quantum mechanics works. When we calculate the behavior of atoms, molecules, semiconductors, or lasers using quantum theory, the predictions match experiments with extraordinary precision. The agreement is sometimes accurate to more than 10 decimal places. Few theories in science have ever achieved that level of confirmation. We know that superposition is real in the sense that it produces measurable interference effects. The double-slit experiment is not a philosophical story, it's a laboratory fact. Quantum states can combine and interfere in ways that have no classical analog. We know that entanglement is real. Two particles can share a joint quantum state such that measuring one immediately determines the correlated properties of the other. even across large distances. This has been tested repeatedly, closing loopholes and confirming that nature violates certain classical assumptions about local hidden variables. We know that decoherence happens when quantum systems interact with their environment. Interference between different components of the wave function becomes effectively unobservable. This explains why macroscopic objects do not appear to be in visible superpositions. A baseball does not smear across the field in a wave like blur because it is constantly interacting with trillions of surrounding particles. We also know what we do not know. We do not know whether the wave function represents something physically real or merely a tool for organizing information about measurement outcomes. Different interpretations give different answers, and so far, experiments do not distinguish among them. We do not know whether collapse is a genuine physical process. Some theories propose spontaneous collapse mechanisms that slightly modify quantum equations. These ideas are being tested, but no confirmed deviation from standard quantum predictions has yet been observed. We do not know whether the universe is spatially infinite. Observations tell us that the observable region is extremely large and very nearly flat. But beyond the cosmic horizon, we cannot directly see. Extrapolations about infinity are logically consistent with current data, but they go beyond direct observation. We do not know how to combine quantum mechanics with gravity into a single, experimentally verified theory of quantum gravity. Our current descriptions work beautifully in their respective domains, but at extreme scales, such as inside black holes or at the Big Bang, our theories are incomplete. And crucially, we do not know how consciousness arises from physical processes in a way that is mathematically precise. Neuroscience has made enormous progress in mapping brain activity to experience, but there is no widely accepted equation that tells us how subjective awareness emerges from neural dynamics. This matters because when people talk about you surviving in branches, they are implicitly making claims about how consciousness relates to physical states. Yet physics, as currently formulated, describes particles and fields, not subjective experience. So honesty demands restraint. The statement, "You're already dead somewhere else," is not a confirmed empirical discovery. It is a conditional statement. If certain interpretations of quantum mechanics are correct, or if certain cosmological models describing an infinite universe are correct, then multiple versions of your physical history may exist. But science has not yet told us which interpretation is true, nor whether infinity is physically realized. What science has done is remove the comforting assumption that reality must align with human intuition. We stand in a position that is both powerful and humbling. Our equations reach astonishingly far, yet when we ask what they ultimately mean about existence, identity, and finality, we encounter genuine uncertainty. And that uncertainty is not a weakness. It is an honest reflection of how far we have come and how far we still have to go. So why does all of this feel so destabilizing? Why does the idea that there may be other versions of you, some alive, some dead, some slightly different, produce such a deep emotional reaction, even when presented carefully and conditionally? Part of the answer lies in how the human brain constructs reality. Your nervous system evolved to navigate a very specific environment medium, sized objects moving at moderate speeds on the surface of a planet. In that environment, ambiguity is dangerous. If you see a predator, it either is there or it isn't. If you step off a cliff, you fall. Clear single outcomes are adaptive, so your brain compresses the world into definite narratives. Events feel linear, causes lead to effects. There is one past, one present, one unfolding future. Quantum mechanics does not respect that intuition. At its foundation, it describes a mathematical object, the wave function, that evolves deterministically and can contain multiple mutually exclusive possibilities at once. The classical world we experience emerges from that deeper structure through processes like decoherence. But the underlying description remains richer than the story our senses tell. There is also a psychological factor tied to identity. From early childhood, you construct a self-model. Memories linked together into a coherent autobiography. You say, I, and refer to a continuous entity stretching backward in time. This narrative self is extremely useful. It allows planning, responsibility, social interaction. But it also creates the illusion of singularity as something fundamental. If physics suggests that what you call your life might be one trajectory among many physically realized trajectories, the narrative self feels threatened. It interprets multiplicity as a dilution of meaning. Yet consider this carefully. Even in a single universe picture, your life is already contingent. It depends on countless microscopic events you do not control. If one neuron fired slightly differently years ago, your path might have changed. The fact that alternatives were possible has always been true. Quantum branching, if real, does not create contingency. It merely gives those contingencies physical realization. Another reason this idea is hard to absorb is scale. When Nicolaus Copernicus proposed that Earth moves around the Sun, it displaced humanity from the cosmic center. Later, astronomy revealed that our Sun is one star among hundreds of billions in the Milky Way, and that our galaxy is one among hundreds of billions more. Each step expanded the stage and reduced our apparent centrality. The multiverse, whether quantum or cosmological, is another such expansion. It suggests that even our entire observable universe may not be the full stage. Our timeline may not be unique. Historically, these conceptual shifts are uncomfortable at first. They challenge instinct and ego. But they do not make human experience irrelevant. They relocate it. There is also a cognitive limitation at work. The human mind is not well equipped to intuitively grasp extremely large numbers, infinite sets, or high-dimensional mathematical objects. When we hear countless branches or infinite space, our imagination substitutes a vague blur. We feel overwhelmed not because the ideas are incoherent, but because our mental hardware was never optimized to simulate them vividly. So the struggle is not evidence that the ideas are wrong. It is evidence that our intuition evolved for survival, not for fundamental physics. What science repeatedly shows is that reality does not adjust itself to the scale of human comfort. Instead, we adjust our understanding slowly, imperfectly, but progressively to match the structure that experiments in mathematics reveal. And when that structure becomes large enough to include multiple versions of our own story, the difficulty we feel may be less about physics and more about letting go of the assumption that our particular thread was ever the only one that could exist. Now we arrive at the most delicate part of the discussion, death itself. In an ordinary single timeline view of the universe, death appears as a hard boundary, a line you cross once, a biological process that, when complete, marks the end of subjective experience. From this perspective, it is absolute. There is one life, one termination point, and that's it. Physics, at least in its current form, does not dispute the biological reality of death. When the brain irreversibly loses the complex electrical and chemical activity required to sustain consciousness, experience stops. There is no scientific evidence that awareness floats free from physical structure. All reliable data we have ties mental states to brain states. But if we take seriously the possibility of branching histories, whether through quantum mechanics or cosmological duplication, then death becomes something slightly different conceptually. In a branching framework, death is not a single global event. It is an event within a branch. Imagine once again that vast tree of reality splitting continuously. At some branches, a particular organism's biological processes cease at age 20, in others at 50, in others at 90. In still others, accidents never occur and different diseases arise. From the outside mathematical perspective, the full wave function contains all of these outcomes. But from the inside, from the perspective tied to one functioning brain, there is only one experience timeline. Here is where confusion often creeps in. Some people hear this and conclude that death is therefore an illusion, or that one will always find oneself in branches where survival continues indefinitely. That conclusion goes beyond what physics justifies. First, probability matters. In the quantum formalism, different branches carry different amplitudes, which translate into measurable probabilities. Extremely unlikely survival scenarios do not become subjectively dominant simply because they exist. The mathematical structure does not privilege conscious continuity in the way some popular descriptions suggest. Second, identity across branches is not something physics currently defines in a rigorous way. Each branch contains a physically distinct brain state. After branching, those states evolve independently. There is no known mechanism that allows a single stream of awareness to hop from one branch to another or to prefer one outcome. If a branch contains a version of you that survives an event, that branch contains its own continuous narrative. If another branch contains a version that does not survive, experience in that branch simply ends. There is no meta perspective that stitches them together into a single immortal observer. So in scientific terms, death remains real and local. It is real within each history. It is local in the sense that it applies to particular trajectories, not to the total mathematical object that might include many trajectories. This reframing does not remove the biological fact of mortality. It does not provide escape. What it does is challenge the assumption that a single observed ending exhausts the full set of physically allowed endings. In a possibly branching or infinite reality, every physically permitted conclusion may occur somewhere in the grand structure. But you, as an experiencing system, are confined to one thread. That confinement is not mystical. It is a consequence of how physical processes unfold. And perhaps the most scientifically honest statement we can make is this: physics expands the stage on which life and death play out, but it does not yet dissolve the boundary between them within any given lived experience. The boundary still exists. It is just no longer necessarily unique in the total architecture of reality. If we take a step back and look at the broader picture, a subtle but profound shift in perspective emerges. In a single universe worldview, life and death feel absolute, as though there is one story and one ending. The narrative is linear, and our sense of self is tightly bound to that singular thread. But if the universe is branching or infinite, then reality itself is far richer than a single unfolding story. Every quantum event, every microscopic choice, and every contingency may generate multiple outcomes, each instantiated somewhere. Life and death become features of individual branches rather than cosmic absolutes. This has profound implications for how we understand existence. Each version of you experiences its own consistent timeline, its own memories, and its own identity. From within that branch, life feels whole and continuous, and death feels final. Yet physics suggests that this is only one trajectory among countless possibilities. The broader structure, the full wave function in a many-world scenario, or the vast spatial ensemble in a potentially infinite cosmos, contains all of these trajectories simultaneously. In that sense, your life is simultaneously unique and multiply instantiated. It is important to recognize the subtlety of this idea. It is not mystical or wishful thinking. It does not imply that you are secretly immortal, or that you will somehow jump to other branches after physical death. Conscious experience appears to be confined to a single physical trajectory. Each branch is isolated from the others by decoherence, by physical separation, and, as far as current science can tell, by the nature of consciousness itself. What makes the multiverse mind-blowing is that the you, who experiences this life, is only a local inhabitant of one branch, while the total reality contains countless other versions, each real in their own right. This perspective changes how we see the nature of probability and contingency. In classical thinking, an event either happens or it does not. In the branching view, both outcomes exist. Some measure of reality follows each path. Your choices, your accidents, your successes and failures are all represented somewhere in the total structure. Yet from your subjective perspective, you are confined to the trajectory that you occupy. The sense of singularity is not violated, it is preserved within each branch. But the larger, more abstract reality is vastly more complex than intuition allows. It also reframes what it means to be central or unique. Historically, humans have found it difficult to adjust to ideas that challenge our presumed centrality. Copernicus displaced Earth from the center of the solar system. Modern astronomy placed our sun among billions of stars. Cosmology suggests our galaxy is one among hundreds of billions. The multiverse continues this pattern. It suggests that our timeline, our version of reality, is not uniquely privileged. It is one among a multitude of equally real possibilities. Yet there is a quiet, almost paradoxical beauty in this realization. While the larger structure of reality may be unimaginably vast and populated with countless alternative versions of ourselves, the experience that matters, the one we inhabit, is this one. Every sensation, thought, and choice unfolds along this trajectory alone. That singularity of experience, even within a potentially infinite or branching cosmos, is what makes life meaningful from the inside. Reality may be larger than we can imagine, but it is also profoundly intimate. This shift in perspective does not diminish life. It situates it. It asks us to appreciate the fragility and specificity of our own trajectory while acknowledging the grand, intricate architecture in which it exists. Life and death, joy and sorrow, meaning and uncertainty are local features of an immense, multiscale structure, a reality far stranger and more beautiful than everyday intuition suggests. The universe and the self within it is at once both singular and multiply realized, a pattern unfolding in ways we are only beginning to glimpse.